Welcome to the deep dive. We're jumping into some core ideas in data science today.
Right. And we're doing it by looking at practice questions from the Dell Data Science Foundations exam, the D-DS-FN-23.
Exactly. It's a neat way, we think, to get a quick, solid handle on these fundamental concepts without getting totally bogged down.
Yeah, for anyone wanting to build that understanding efficiently, this should be helpful. We're looking for those insights that make things click.
Okay, so just for context, that exam, it's multiple choice, about 60 questions. You get 90 minutes, need 60% to pass. But our goal here isn't just, finding the answers. It's about digging into why they're the answers, what data science principles are really being tested.
Let's do it.
Okay, first question then. What type of machine learning task is used when the target variable is continuous? Options are classification, regression, clustering, association.
And the correct answer there is regression.
Regression. Okay, we hear that word a lot. What makes it the right choice when the target is continuous?
Well, continuous is the key. Regression is what we use when we're trying to predict a numerical value that can exist on a spectrum.
Predicting a house price?
Right.
Or maybe temperature.
Exactly like that. Or customer lifetime value. It's a number, not a fixed category. And actually, deciding which regression technique fits best often needs a bit of upfront data exploration.
Right, so it's different from classification, where you're putting things into boxes like spam or not spam.
Precisely. Classification gives you a label. Regression gives you a quantity. And stepping back a bit, regression falls under supervised learning.
Meaning we train it with data where we already know the right number, the right answer.
That's it. The model learns the relationship between the inputs and that continuous output from labeled examples.
Okay, makes sense. Solid start. Question 2. In the discovery phase of the data analytics lifecycle, which activity is typically performed? Choices. Monitor model accuracy, identify business goals and define the problem, evaluate model performance, present findings.
The answer for this one is B. Identify business goals and define the problem.
That feels, well, pretty fundamental, doesn't it? Like step one for almost anything. Why emphasize it in the analytics life cycle?
Because it truly is the bedrock.
Yeah.
Before you even think about algorithms or data cleaning, you have to know what you're aiming for. What's the business need? What specific problem are we actually trying to solve here?
So really nailing down the why before jumping into the how.
Exactly. It's about defining the problem clearly, making sure it aligns with what the business wants to achieve, and starting to think about, well, what data might we even need for this? It guides everything that follows.
Got it. Okay, question 3. Visualizations. What visualization is most suitable for showing the distribution of a single numeric variable? Scatterplot, pie chart, histogram, box plot.
The best fit here is the histogram.
Histogram. Okay, the one with the bars, usually touching. What does it tell us about distribution specifically?
So a histogram is great for getting a quick visual feel for how your numerical data is spread out. It groups the values into bins or ranges. And then the height of each bar shows you how many data points fall into that specific range. You immediately see the shape. Is it symmetric, skewed? Any weird gaps?
You mentioned bins.
Yeah.
Does how you set those up matter?
Oh, absolutely. The number of bins or their width can really change how the histogram looks. Too few, and you might miss details. Too many, and it can look messy. It's a bit of an art sometimes.
Okay, so for one variable spread, histogram is the go-to. Briefly, when would you use the others, like a scatter plot?
Well, a scatter plot is your tool for looking at the relationship between two numeric variables. Pie charts show parts of a whole, maybe less used now. Box plots give a summary showing quartiles, median, outliers, also good for distribution, but in a different way.
Understood. Moving on, question 4. Which technique helps reduce overfitting in a model? Options: adding more input variables, increasing iterations, using a very deep decision tree, or cross-validation.
The technique you want there is cross-validation.
Overfitting, that's like when the model tries too hard on the training data. Is that right?
That's a good way to put it. Yeah, learns the training data, including all the noise and random quirks, so well that it looks amazing on that data.
But then falls flat on new data it hasn't seen.
Exactly. It's like it memorized the answers instead of learning the concepts. It doesn't generalize.
Okay, so how does cross-validation help fight that?
Cross-validation is a pretty clever technique. Instead of just splitting your data once into train and test sets, you split it into multiple parts or folds.
Okay.
Then you train and test the model multiple times. Each time, you hold out a different fold for testing and train on the rest. By averaging the performance across these different test sets, you get a much more robust estimate of how the model will actually perform on unseen data.
Ah, so you're testing it on different slices of the data to make sure it's not just getting lucky with one particular slice.
Precisely. It forces the model to learn patterns that hold true across the data, not just idiosyncrasies of one specific training set.
Smart. Okay, that leads nicely into question 5. What is a key characteristic of a good predictive model? Options. It generalizes well to unseen data. It has the most complex structure. It fits the training data with zero error. It requires extensive manual intervention.
The key characteristic is definitely A. It generalizes well to unseen data.
That word again, generalizes, seems like the ultimate goal here.
It really is. I mean, what's the point of a model if it only works on the data you already have? You build models to make predictions or decisions about new situations, new data.
Right.
So that ability to take what it learned from the training data and apply it accurately to fresh data, that's generalization, that's what makes a model useful.
So chasing zero error on the training data isn't the goal. It might even be bad.
It can absolutely be a red flag.
Yeah.
A model that fits the training data perfectly, especially a complex one, is often overfitting. It's memorized, not learned. You need that balance, capture the real patterns, but don't fit the noise.
Okay, clear. Question 6. In which phase of the data analytics lifecycle is model deployment planned? Model building, data preparation, operationalize, or discovery?
Deployment planning happens in the operationalize phase.
Operationalize. Sounds practical, like putting it into action.
Exactly. This is where you figure out the nuts and bolts of getting your model out of the lab and into the real world. How will it integrate into the existing business processes? What systems will it interact with?
Like putting a recommendation engine onto a website.
Perfect example. Or embedding a fraud detection model into a transaction system. Planning how that deployment will actually work, monitoring it, maintaining it. That's all part of the operationalize phase.
So it's about making the model actually do something useful in the business.
That's the whole point, yeah. Value comes from deployment.
Right. Question 7. Dealing with data types. What is a common method for encoding categorical variables for modeling? One-hot encoding, normalization, feature hashing, PCA.
A very common one is one-hot encoding.
Categorical variables.
Yeah.
Remind us. That's like product types or city names, things that aren't numbers inherently.
Exactly. Things that fall into distinct categories. And since most models need numerical input, we have to convert these categories. One-hot encoding is a standard way to do it. And just quickly, PCA there is principal component analysis. That's more about reducing dimensions.
Okay, so how does one-hot encoding work then?
Well, let's say you have a color column with red, blue, green. One-hot encoding creates a new column for each category. So a colored column, a color blue, a color green.
Oh. Cool.
Then for each row, if the original color was red, the color red column gets a 1, and the blue and green columns get a 0. It turns categories into binary flags.
Got it. Simple enough. Okay, question 8. Which technique is commonly used for unsupervised learning? Decision trees, linear regression, k-means clustering, logistic regression.
For unsupervised learning, the answer is k-means clustering.
Unsupervised. So unlike supervised, where we have the answers, here the data is unlabeled.
That's the key distinction.
Yeah.
With unsupervised learning, you don't have a predefined target variable you're trying to predict. Instead, you're looking for inherent patterns, structures, or groupings within the data itself.
And k-means helps find those groupings.
Exactly. K-means is probably the most well-known clustering algorithm. Its goal is to partition your data points into a specific number, K, of clusters, where points within a cluster are similar to each other and points in different clusters are dissimilar.
So it finds the natural clumps in the data without me telling it what the clumps should represent beforehand.
You got it. It lets the data speak for itself in a way.
Interesting. Okay, question 9, getting into statistics. Which statistical test would you use to determine if there is a significant difference between two group means? T-test, chi-square test, z-score test, correlation analysis.
That would be the t-test. Answer A.
T-test. So comparing means averages of two groups. Give me an example where you'd use that.
Sure. Imagine you run two different versions of an ad, A and B, and you want to know if version A resulted in significantly higher average clicks than version B.
Okay.
Or maybe you're comparing the average test scores of students who use two different study methods. The t-test helps you figure out if the difference you see in the averages is likely real or if it could have just happened by random chance.
So it separates a meaningful difference from just statistical noise.
That's a great way to think about it, yes.
Yeah.
Is the difference statistically significant? The t-test helps answer that for two group means.
Right. Final question then, number 10. What is one primary advantage of using cloud-based analytics platforms? Fixed cost, scalable computing resources, guaranteed higher accuracy, no need for data security.
The big advantage highlighted here is B, scalable computing resources.
Scalability. We hear that word constantly with the cloud. What does it mean practically for data analytics work?
It means flexibility, essentially. Cloud platforms let you easily increase or decrease your computing power, make processing speed, memory, storage as your needs change.
So if I suddenly have a massive data set to process or a really complex model to train.
Exactly. You can spin up more powerful resources temporarily to handle that big job. And then when you're done, you can scale back down so you're not paying for resources you aren't using.
Which avoids having to buy and maintain a ton of expensive hardware yourself just for those peak times.
That's the core benefit. It offers huge flexibility and often makes complex analytics more cost-effective, especially when workloads fluctuate.
So maybe a final thought for everyone listening. Now that we've walked through these building blocks, what real-world problems or situations do you look at differently, through a data lens? What questions come up when you think about applying some of these ideas to data you see day to day?
Yeah, definitely something to ponder.
Well, thanks for joining us on this deep dive.